Look weird shaved. Alright people, as you can see, the Project Ute's still here. That engine's still sitting on, nope, you can't see that. That engine's still sitting on wood over there. There's no space to pull out and work on any of the other projects. So we're gonna run to the store and spend some time on the computer today. Let's go. Okay, so we have returned from everyone's favorite hardware store, Harbor Freight. You can see part of what I'm dealing with here, and this is a new push for me to organize my life. So we're gonna give it a shot. So we got a bunch of crap over here, but this stuff is all brand new. I bought some wheel chocks because I've been working this entire time on one piece with like a couple pieces of 2x4s, which is maybe not the safest thing ever, so we got some wheel chocks. But up here, we have a bunch of wheels. So these are caster wheels. This is a big, huge caster. This is gonna go on, this is what I'm gonna go put on our engine stands that we're gonna fabricate for you guys here. So wanted to show you guys that. This will go on those bottom rails. But we got these smaller casters, which are gonna be on today's project. These are much smaller, obviously, so they don't have nearly the weight capacity of those. Those have a weight capacity of 300 and something pounds per caster. These ones are more like 60 or 80 or 100 or something like that. Much less capacity. But these aren't going to be for something like a full-blown V8 big block. They're actually going to be for these. So I don't happen to have a little, fork hydraulic loading thing to move this stuff around. And even if I did, I probably wouldn't be able to use it to move this stuff on that. Into and underneath here where I'm going to store all of my sort of big components and engines, because that space is obviously taken up with crap. So we want to try and solve our storage solution problems with these two items. So we got our engine block here and attached associated accessories for the RX8. This is a Renesis. This is our old one that we'll eventually rebuild for you guys or sell or do something with. And then our spare transmission for the RX8 as well. And I thought this would be a great time to test the full capabilities of my big, huge 3D printer. And also test some material and see if it actually matches up to the computer simulations. So I'm gonna go put this back down because I don't need this anymore. And still dirty as hell. I'm gonna go get on the computer and I'll meet you guys there. Are we here? Is it going? Looks like it's going. Okay, everybody. We are back at my nerdy desktop here, showing you kind of what we came up with for a design. And it's, if the computer models are to be believed, it's actually a lot more robust than I was expecting. So I'm going to open up our SolidWorks here. I don't know why it's save. Don't freak me out here, SolidWorks. This is a trolley design, or a flat plane, whatever. It's designed to have parts or wood put over top of it, and then heavy parts go down on it. So it's pretty basic, straightforward. This uses some principles design. If you guys have ever seen like a roll cage or something like that, you know that triangulation is a way to provide strength and stiffness to otherwise flat, open parts, where this whole thing would flex a lot more along the edge if none of this interiorness was here. But it lets you provide that stiffness using a minimum amount of material. Usually that's because of weight. It's a weight thing. But in this case, it's actually, we want to minimize the amount of material, because the more material we put in something that's 3D printed, the longer it takes to 3D print, and this is already pretty big. So we'll get a little top view here. So as we look at this thing here from the top plane, some of the basic dimensions, it is 21 inches long by 14.5 inches wide. And it's essentially a perimeter of 2-inch material with the interior lattice work running from the nodes in the center lines here, so that all of the stresses should be carried relatively straight into the caster locations. So all of these run and connect these parts and these center lines here, try and keep everything as stiff as possible. Couple things to note here. For 3D printing, we have added a bunch of chamfers, and what this does, oh crap, I missed one, hold on. Edit feature. Oh. There. That one. And that one. Gosh, it's hard to see all those edges sometimes. We'll fillet all of these items again. So we've added a bunch of fillets and chamfers in here, and what that does is it gets rid of the hard edges. So without the chamfers, this thing, come here, looks like this. And 3D printing these corners and these corners is actually pretty difficult and can create a lot of issues. Further, one of the basics of design is sharp changes in direction like this are stress risers, such that they actually significantly, by many factors, increase the amount of stress that would be seen in these connection points, like say, this line here. So what we do to make it both easier on ourselves and a better overall part is we add a bunch of chamfers, and we try and chamfer most of the edges just to make sure that we're getting the best part and the strongest part and the most durable part that we can. So this is kind of, I want to show you guys something here. So part of this project is just a fun idea to check out the capabilities of our printer printing big things, and also to take a bit of get a little bit of confirmation on our modeling here. So what I actually did is I created a couple of static stress models on this thing. So we're going to open up static 1 here. Rerun this study, please. So what this does, SolidWorks and most good CAD programs, Autodesk Fusion 360 has similar features, I do believe. Solid Edge, CATIA, they all have some ability to do this sort of simulation. It is actually making a mathematical model of our thing here, and then it creates a mesh, and then applies forces to it, and tells us where all the stresses and strains and how much deflection we're going to see with this thing with the applied loads. So as this thing is merging and getting the mesh right, the idea here is I wish this thing was out of the way. The idea is before you go build something, you want to be able to test whether it's going to hold the forces you think it will. So what you do is you have a program like this, which can create a mathematical model and actually check the strength of your piece before you go build it and spend a bunch of time. And I'll show you why that can save you some issues here when we get into the slicer, and just how much time it's going to take to print one of these in a full complete form. So here's our stress graph. So if you look at this on the right hand side, this is kind of like your lowest stress at the bottom is blue, your highest stress at the top is red, and these numbers are one measurement of stress, newtons per millimeter squared, and it's a PSI essentially, but it's measuring something somewhat different. So I do it in megapascals just because a lot of the documentation on 3D printed materials is in is in megapascals and that sort of thing. It's not usually in PSIs. Otherwise, I just have it convert this to PSI. But what this is showing us is that when we load this, and so this external load is a pressure load, so an evenly distributed pressure load on this member and this member. When we load it like that, what the stresses do is they actually are basically non-existent in the centerpiece. So you can see in this loading configuration, we'd actually be much better, or we'd probably be just fine with with none of this central lattice work in here. This lattice work is in here for a reason, and I'll show you that in static 3 when we get to it. So this is a load on just these two ends. This is kind of simulating how I expect the transmission to sit on this. So I expect its load to be here and here. I expect to be relatively evenly distributed. So that's what this is here. And I've actually put this load, this is a 10.34 psi load. What that equates to is actually 400 pounds. So this is 400 pounds of load evenly distributed across these two members. And what we're seeing is stresses, maximum stresses, at 24.39 megapascals. And when I was saying earlier about stress risers, so the actual maximum stress occurs right here on this edge. So this is one of, and it occurs at each one of these outer edges, here, here, and then on the bottom here and here. It occurs at pretty much the same spot. So this is a huge stress riser in this part, because of the sharp edge. It actually hugely increases the stress at that point. But I'd like to show you guys that this piece with 400 pounds of load on it is only at it's only calculating out to maximum stresses at 24.39 megapascals, where PLA, at least if you go look at like Ultimaker's PLA data sheet, they advertise PLA with a yield strength, which is it's a technical term, but it really means when the plastic starts stretching permanently, because plastic can stretch and return to its same shape. When it starts stretching permanently is 49.5 megapascals. So even with 400 pounds of load on this thing, on only these two pieces, this 3D printed PLA only plastic piece is actually holding up pretty well. We're gonna go on. Static 2 is a static, it's the same thing, only I did the load in pound-feet. I wanted to make sure I was getting my pressures right when I was doing my math. And then this is the really cool thing. So why use 400 pounds? Well, the RX8 engine, the Renesis engine, weighs 142 kilograms. Hold on, let's look this up. Renesis engine weight. The Renesis engine has a weight of 112 kilograms, or a mass of 112 kilograms, where it weighs 247 pounds, give or take, with standard attachments, but not things like the starter motor and things like that, and no fluids. So 400 pounds is already giving us an extra 150 pounds of weight to see if we can hold a Renesis style engine on this 3D printed PLA only piece. This is a load kind of how we expect the engine to sit on it. So if we were to use the same thing, which was originally designed purely to move the transmission around, and store it as low as possible to the ground. But if we put the engine on this piece, and probably in order to do that, we'd put a plywood piece over this, so that it has something solid underneath it in case it leaks or anything else, and just distribute the load around. So if we put a plywood piece over it, which is essentially negligible weight, and then set the engine on and equally distributed the load, we'll run this study again. And so we run that and we get something that looks like this. So our stresses go down, maximum stresses go down. We tend to spread the stresses out a little bit, and although your maximum stress areas are still in the same spot. And we get more deformation through the center, as would be expected. But really what this model is telling us is that if the material properties of PLA that they give you on the data sheets are close to what you can get 3D printing a functional component out of it, we should be able to take this basic PLA 3D printed piece using standard hobbyist material and put a very heavy motor on it and run it around. Although a piece this size does present a few problems, which we're going to go over now as we get into our slicer software. So here we are in our slicer software. This is Idea Maker for anyone who hasn't seen this before. And Idea Maker essentially takes that model that we created there and digitizes it in a way that the 3D printer can understand. So this is the model. You notice that our printer bed is only 12 by 12 by 24, yet this thing is 14.5 inches wide. So what we actually have to do in that case is rotate it around and print on the diagonal, and it'll print in your print bed. So just because you have a 12 by 12 by 24 or a 6 by 6 by 10, whatever size your printer bed is, you can get creative with your positioning and actually print something. It would actually be ideal to print this probably on more of a slight angle, like bring it up in this location, just because we might be able to get rid of some of these support materials, but we don't really have a ton of room to rotate it like that. So in the end, we're just going to leave it in the straight up and down, which is good for a couple reasons and bad for at least one more reason. So, oh, I didn't get rid of that support material. Oh well. We print this up and down because, well, one, we have to in order to make it fit. But two, remember a few videos ago we were talking about, let's open up the preview here, talking about designing for manufacturing and designing so that your part is manufactured in a way that makes it beneficial to load it in the manner you expect to, or at least makes it most resistant to the loads you expect to put on it. In this case, most of the loads we expect it to see are in the result in this load. We expect most of the loads to end up here, but we have some loads in this direction, the Z direction, I think, on this, yeah, and in the X direction. In our transmission load case scenario, you see pretty much all the load is being carried right here. So in the transmission, and we could even load our engine in this way so that the load's mostly carried in this Z direction, we would want to have continuous strands of plastic in that direction, which, as we go here, let me take a few layers off and zoom in. This is a lot of layers to deal with on something that's this small. So you can see that what we're actually doing is we're creating a shell where all of the strands of this particular design are in our where we want our loads to go transfer. So they're transferring the loads along continuous strands, relatively speaking, to our caster locations, which are our fixed locations and where all the weight is going to go down into the ground. So this gives the part the maximum amount of strength in our transmission load scenario. It makes it a little bit more sketchy for the engine load scenario, where a lot of our deflection is going along this axis here, and that might cause some separation in the layers, but there's not a lot of stress there, so it may just be deflection for deflection's sake. One of the things that is problematic with the design as is that we have a lot of overhangs and 90 degrees and surfaces printed out of the midair, right? So if we print this vertically, all of these reliefs that we use to cut down on material, the final part, they still have to be filled in here and here and here and here and in some of these parts here, so that those 90 degrees and all these big corners can get printed, because otherwise they'd just be big globs coming down here. So we save some material. You can see, like, even these pillars, these support pillars, are not as dense or as thick as what you would find in these actual structural members, but they are not air gaps like this, where you're saving yourself the material. So that brings us to something that is a concern when you're building big parts on 3D printers. So those of you who have something like the Creality CR10, this is a concern for you. Notice up here on the left hand side, this thing will take 139 hours to print. 139 hours. That is 5 days, I believe. Just short or just above 5 days. That is a 5-day print. And admittedly, it uses 2.3 kilograms of material. So each one of those spools, your typical spool size is 1 kilogram. So it'll use basically 2.5 kilograms of material, 2.5 spools, in order to make this part. But the real kicker is that production time. So these are very long prints, and it's hard to get away from long prints in very large 3D printers. So 5 days is actually not a terribly long print. If we were printing something that filled up most of the volume of this printer, we could easily be looking at prints in the 7 to 10 day range. In fact, before an earlier version of this piece, it was 1 inch thick instead of 3/4 of an inch. So the stresses were a little bit less because of the way bending stresses work. But that was 175 hours, this print time. But I do want to show you guys a trick that you can use if you have a printer that has adjustable nozzles like mine does. So I can go in here, we'll slice this again. We're gonna go, and I just gotta adjust this thing. I have a 1mm nozzle available to me. So what a 1mm nozzle does is it puts out more material per pass. And this is just a setting that I have for 1mm nozzles with a certain support. So we'll slice using that. So remember 139 hours? Yes. Yes. This thing is now 42 hours. So we've saved 97 hours of print time. So we've more than cut it in half just by going to a larger nozzle. So what it essentially means is instead of 2,300 layers, and this preview is going to go a lot faster, of material, we have 716 layers of material. So that's a trick that you can use to get some of your print times down. If you print with a much bigger nozzle, you can definitely cut your print times into a more manageable level. So we're gonna go throw this thing into a printer, and we'll see you guys back on this video in a couple days. And there she goes. Unfortunately, as you may or may not be able to tell by the tiny little layers on this thing, I did not have the right size nozzle that I thought I did, which means this print is going to take 5 days instead of a day and a half. So that's not going to be super awesome, but by the time the print head that I wanted to come in would come in, it would also take about 5 days. So I figured I might as well start printing, and then we can run a test in the next video on this stuff that's printed with a very small nozzle, and then we'll print one with a big nozzle and see if it runs any differently, which I think might be kind of interesting. Since we're gonna need 2 of these anyway, might as well print 2 with different nozzles and see how it goes. So anyway, guys, thanks for watching. The Chrysler is still here. You would not believe how hard it is to try and get someone to buy something like this that has a lot of money in it for a junkyard. But I don't know, like Pick and Pull wouldn't buy it. I don't know. There's something. This is a lot harder than I thought to get someone to buy a car. But this is still here, so a lot of my garage stuff is on hold for a minute. So these next few videos, I'm sorry if you're hoping for car stuff, those will come back as soon as this guy gets out of here. But we're gonna try and organize our workshop area because we are gonna have to get very organized for the winter where we do some real fab work. And I've got a bunch of tools and boxes I haven't shown you guys yet, so we'll start organizing and getting that stuff all made up for you in the next video or 2 while we're trying to get this car out of the way. So until then, thanks for watching, everyone. My name's Andrew. This is another Make and Break YouTube channel video. If you like the video, hit like. Comment if you have questions, concerns. Did I miss something? Let me know. I definitely pay attention to the comments and try and answer each and everything I see. And then if you like what we're doing on this channel, subscribe. We do 3D printing videos like this, a lot of car videos. You go check some of our stuff. We just pulled the engine out of our formerly Project Ute Chrysler 300C, so that's going to go into another project at some point in the future. And yeah, so thanks for watching, everyone, and we'll catch you later.